Hello everyone, welcome to our talk. It's called, like you just heard, a bit redundant, How the Metrics Backend Works at Datadog. I'm Adam Mckaig and I run an SRE team at Datadog called Metrics Reliability. Before Datadog, I was on monitoring SRE at Google a couple of years ago, where we looked after Monarch, which is the big planet scale monitoring thing that they have. I really like big distributed systems and such, and problems with them, which is why I'm here today to tell you about one of them. That is me and a dog. It isn't my dog, but we are friends, and she's just looking away and pretending she doesn't know me. And this is Tahia.
Hello, I'm Tahia. I'm an SRE at Datadog. I also work on the Metrics Reliability team, which makes Adam my manager. I'm based out of Toronto in Canada, and this is my dog, and she's really great. Okay, moving on. So Datadog is a suite of cloud observability products. You sign up, you get an API key, you download the agent, which is a piece of software you run on your machines or VMs inside your firewall, and it collects a bunch of interesting data about the services and the apps running on the machine and sends it over to us. This includes metrics like logs, includes things like metrics, logs, traces, etc. Then we store it, aggregate it, and make it available for querying on our web interface. In terms of scale, we're a multi-cloud. We run on hundreds of thousands of K8s pods, and we ingest tens of trillions of events per day, which is a lot of data. We're giving this talk because Datadog spent a bunch of time and effort learning how to store and serve all this data reliably while also growing rapidly. Some of the problems we've encountered and our approach to them might be applicable to your services, so we'd like to share them with you. But before we get into problems and solutions, I'm going to give you an overview of how Datadog works under the hood. So roughly speaking, Datadog has 4 separate parts. There's intake, storage, query, and web. Datadog is essentially a big data store, and this is a pretty common architecture for big data stores. It might look a little weird to you, though, if you're more familiar with the 2-tier web app in front of a relational database type of system, like a Rails app or a Django app. If that's more what you're used to, you can think of it this way. The web tier is the same, and the other 3 are equivalent to your database tier. Our storage tier is your low-level storage, which deals with literally storing bytes into files on disk. And our intake and query tiers provide a higher-level interface for accessing that lower-level storage tier. Here's everything again, but zoomed in. And don't worry if you can't read everything yet. We're going to zoom in further. The part that we think of as metrics is circled here, and today's talk will do a deep dive into the storage bits, but right now I'm going to try and do a speed run explanation of all the other stuff around it. So there's a storage tier in teal, which I'll come back to. On the left, we have, in purple, we have the intake tier. There's an ingester service that receives all of the incoming data from our agents and API clients, performs authentication and basic validation, and then writes it to an elastic Redis cluster that we call the intake queue. Next, it performs resolution, which involves transforming strings like system.cpu.usage into indexable keys. We store these mappings in a big Cassandra cluster with a cache in front of it, and then after resolution, we write everything into one of our Kafka clusters in the storage tier. Now, from the other side in blue, we have a pretty standard web tier. This serves the web interface and forwards data requests to the backend. It's a really interesting web app, but it's out of scope for today. Between the web and storage tier in pink is the query tier. This receives those high-level queries from the web, fetches the relevant data from the storage tier, and then aggregates it as needed. And then for the rest of the presentation, we're going to focus on this part, the storage tier in teal, and a couple of its upstreams. When people ask, how does Datadog work? The answer is going to be right here. So we're going to use the index and point services as our main Kafka consumer examples. There are a lot of other ones too at Datadog, but we won't get into them in detail today. The index service consumes all of the incoming data and uses the tags it sees to build a giant index of individual tags to the contexts which contain them. A context is our name for a unique combination of tags. You might ask it for something like, for example, for customer X, give me all of the context IDs with the tags service equals foo and data center equals bar. The point service stores points and is optimized for query performance, and that's the one right below index there. The interface is low level, and you might ask it something like, give me all the points for customer X, metrics Y, in time range Z, matching this list of context IDs. When combined, these two services allow the query tier to fetch points by customer, metric, and tag, which is what we actually want, and send that back to the web app. We're going to zoom in for even further, but first I need to go a bit over a bit about Kafka so that the rest of the presentation makes sense. Okay, so Kafka is a popular open source distributed message bus. Think replayable PubSub. Our storage tier is built around it, and so understanding some of the terminology is going to be important for the rest of this talk. In terms of the data model, the main thing you need to know is that there are topics, which are then further bucketed into some number of partitions, and partitions of the same topic can live on separate nodes, which is why Kafka topics are distributed and scalable. Producers push messages onto partitions, and consumers can subscribe to topics and pull messages off of the partitions. We'll also be using the term shard a lot in this presentation, which is our own term that we use a lot at Datadog for a consumer that reads from one or more partitions on a specific topic. So to illustrate this pattern, on the left is a Kafka topic with n partitions. Here we can see the first three. And then on the right, we have our two favorite consumers, index and points. Each of these services are made up of a bunch of shards of that service, where each shard handles reading from a particular set of partitions. So you can see that index is reading the partitions into two shards, and points is consuming the same partitions into a single shard. That's fine because different services do different amount of work for each payload, and so they might be grouped differently. Again, there are many consumer services, not just two. We're using points and index as our examples. So when we when we receive data at intake, we need to figure out which Kafka partition to write that data to, which in turn determines which storage shards that data ends up on. We call this a Keyfunc. Here's the very first way Datadog approached this. To determine P, which is the index of the target partition, we take a hash of the customer ID, then modulo that by n, which is the number of partitions, leaving us with the partition index that the customer should be assigned to. This is simple and works really well because our writes at this and reads at this point only ever happen within a single consumer. So one customer, one partition. Adam.
Thanks. So now that you know how Datadog works at a high level, let's talk about some of the reliability problems that we've faced and how we've addressed them through the years. First problem, one you're probably all very familiar with, is that failures happen. And they happen at basically every level. Nodes fail, AZs fail, Kube clusters fail, whole regions fail, or whatever. To our customers, it just looks like Datadog is broken, which is unacceptable, regardless of whose fault it actually is. So to be highly available, we need to be resilient to these types of failures. So let's go through some. Starting with the simplest case, which is node failure. Here's a diagram of a very simple two-tier system, much simpler than the actual system we're describing. You got all these stateless nodes at the top serving traffic, and any one of them could fail without very much impact on your system. You bring up a new node to replace it, which hopefully happens automatically. But behind the scenes, they're all talking to this one stateful node you can see at the bottom, like a relational database or one of our storage nodes. And when that fails, there's not really a lot you can do. It's an availability bottleneck because the data only exists in that one place. So we've got to do something a bit smarter here. To be resilient to that kind of failure, we basically have multiple replicas of each consumer shard doing exactly the same work so that we can send queries to either one of them. We keep those nodes under 50% utilization, so if one of them fails, we can just send all the queries to the other node. This is very obvious. It's almost so obvious that it goes without saying. But it's more interesting when you consider where exactly we put those replicas. Tahia?
Yeah, so let's consider a bigger type of failure, AZ, or availability zone failure. We just said that we replicate our data onto multiple nodes, so any one of them failing isn't a complete catastrophe. So we don't need to worry about individual nodes as a failure domain. But that isn't the end of the story because, oh no, both of these nodes are now on the same AZ. Being robust against individual node failure is great, but if this one AZ starts having problems, your data is going to be unavailable because all of the nodes fail together. What we're getting at is that data exists in nested and overlapping failure domains. We solved this particular problem using zonal replicas, which means in addition to replicating our consumers, we make sure that each replica is running in a different AZ. So that when the AZ gets degraded, we know there will be a second replica to pick up the slack. So, we're still good here.
So we talked about AZs failing, but what happens if a whole Kubernetes cluster fails? A lot of the time we run nodes in multiple AZs, but they are still running in the same Kubernetes cluster. And that is a thing that happens occasionally at our scale. We handle that by using a totally separate Kubernetes clusters per AZ, and we put a replica in each separate cluster. That is it's a tricky trade-off, and it might be the wrong trade-off for you complexity-wise, because it does make rollouts a lot more tricky. And it's pretty hard to break a whole Kubernetes cluster. They're pretty resilient, but it does happen occasionally. And what about regions? Even when you are running multiple Kubernetes clusters, if they're running in the same region, occasionally entire regions get degraded. Replicating between regions is way more complex, and it's way more expensive as well because of egress costs. But it is possible to do this exact same thing, replicating into multiple regions. And in some cases, it's the right choice. And even, it must be pointed out, entire cloud vendors do fail occasionally. There's a link here. We didn't really have time to draw a slide. There's a link here to a global outage that GCP faced a little while back with their authentication layer, and it sucked. The point here is that there is always a bigger or weirder failure domain to consider, and it doesn't mean you've got to solve all of them. We architect our systems to be resilient to the failure of nodes, the failure of AZs, and kube clusters, and a few other domains. So customers shouldn't see those types of failures at all. And this puts a lot of constraints on how we can build things and how we can run things, but we make that choice willingly to gain the resilience. And another point here is to think about these failure domains. The main point really is to think about these domains that your service exists in, and whether you're willing and able to endure failures when they do fail, and what you can do to mitigate. So in addition to hardware failures, and failures in general, one of the first major architectural problems that we faced at Datadog was having too many customers. Oh no. So the storage tier had a single Kafka topic at the time, which was getting really, really big with all those customers in it. And we're talking petabytes here, which is a few years back, that was a lot for Kafka, and it was really hard to operate a Kafka cluster at that scale. But it wasn't just Kafka. Each of the consumers that we mentioned in our storage pool was also in basically one big pool behind that big Kafka cluster, and we really needed to break it up. And most stateful systems, this isn't just us, most stateful systems do reach similar bottlenecks. Maybe for you, it'll be like your one huge Cassandra cluster or your one huge relational database, or maybe even a table within that database. But sooner or later, you've got to architecturally change from this pattern of having one big thing that everything goes in into multiple smaller things. So to illustrate this at a very high level, here is a very simple diagram for box. We have a bunch of work in it. It doesn't actually matter what this box represents because it's like an abstract failure domain, right? And guess what happens when it fails? That's right, literally everything is broken because it's all in the same failure domain. We all know better than this, right? We know not to put all of our eggs in one basket. So we can drastically improve this situation in theory by breaking up that one big failure domain into multiple smaller domains. They're all exactly the same, they're just smaller. So even if we don't reduce the actual chance of failure at all, we do reduce the impact of it by splitting it up in this way. But actually doing that, it's easy to show these boxes, but actually doing that in practice can be pretty tricky. So back in our actual system, we are safe against node failures, AZ failures, because of the stuff we just talked about. But we're vulnerable to that Kafka cluster failing, that big teal stripe there that covers everything. So to reduce that risk here, of course, we split that cluster into multiple Kafka clusters, each one of which has its own topics and its own pools of consumers behind it. We're showing just two here, A and B, but there are many of them, of course. Each customer is sorted into exactly one of those topics. So when the customer sends us a query, we know which cluster, their data can be found in. And how do we do that? The sharding scheme, again. We already showed it, but there was something that we didn't mention. The partition here, P, is variable, but the topic was always a hidden constant. And it's always the same value, of course. But it didn't have to inherently be the case. It was just how we happened to build it. So instead, we can do basically the same thing that we do for partitions. So for a given customer, we first hash mod them into a topic, and then immediately afterwards, we hash mod them into a partition inside of that topic. So the result, even though the clusters are they're configured the same way, is smaller Kafka clusters without a lot of extra complexity at all. And we think there are two lessons here. The first is that you might not need a really fancy sharding scheme. Hashing is great. We love hashing because it's very simple. So long as you can find a convenient sharding key, like we did customer ID, for which your reads and your writes sort of naturally exist within, you might just be able to take your entire workload and then just smash it up into as many layers as you need in order to gain resilience. We shard work into 2 layers, the topic level and the partition level at Datadog, but it would probably work for a 3rd and maybe a 4th layer too. It's a really flexible pattern. The second thing that we noticed is that it was really hard work for us to go from writing to 1 Kafka cluster to writing to n of them. And it was the same thing with querying 2 nodes instead of querying 1 node, and the same thing again with querying like a lot of Kube clusters instead of like the 1 Kube cluster where everything lives. The underlying problem here that we discovered is that we'd sort of baked in too many assumptions that there was only like one other thing, 1 topic, 1 cluster, 1 bucket, or whatever, or 1 sharding scheme for that matter. So even if all of your data does fit today in 1 data store, like ours did back then, consider splitting it into more than 1, like ahead of time. Moving from 2 to 3 is a piece of cake compared to moving from 1 to 2, and it has all kinds of secondary benefits as well. It's much easier to do that when the topic isn't on fire. Like doing it ahead of time would have maybe been smart for us in hindsight. Tahia?
So now we come across our next problem when customers are too big. It's a great problem for your company to have, but not so good for your hash-based sharding scheme. I'll show you why and how you can handle them differently. So here we have points being written to a Kafka topic from intake. Each of the rows in the topic are a partition. The point stat is hashed by the customer ID that submitted it, which should spread the points evenly across the partitions if the customers are evenly distributed or roughly the same size. Here it looks like customer 2 is a little bit different. Turns out it's a big customer. They start writing way more data than all other customers, which ends up gumming up the partition. Even though the number of customers is the same, the actual work being done by that 1 partition is much greater. Let's look at how this affects the consumers of this partition. So here we see our 2 services reading from the topic, 4 partitions into 2 shards each. There's partition 2 with the extra load, and that load cascades to the shard reading from P2 on the index service. It's now overloaded. So to handle this, we can take the work currently being done by that shard and split it in half. We could easily do that here because the overloaded shard is handling both P1 and P2. So here we split that hot shard, meaning we created 2 nodes where there was initially 1. Now each node does half the work. So we're good now. Here's the pro tip from this section. When partitioning workloads, consider using way more shards than necessary and then grouping the shards together. That way you can split them apart again without actually changing the sharding scheme at all, which is very convenient. But oh no, there's another problem. Eventually we've done all we can to split the consumers, and now we're left with a single partitioned consumer, i.e. a consumer that only reads from 1 partition, since that's the smallest unit of Kafka that you can consume from. If that 1 partition is too hot, you've hit a wall because you can't split this. You'll need to consider a different solution. The problem that I just showed you is a side effect of our sharding scheme, i.e. the Keyfunc we showed from earlier. This function, by definition, always puts a single customer into a single partition, no matter how big or small they are. It's nice and simple and lets our consumers remain dumb, which is a good thing that Datadog wants, and it works great when there's an even distribution of customer sizes. But once one of them becomes really big and starts scaling beyond what a single storage consumer node can handle, we have to change the scheme so that 1 customer can be spread over multiple nodes. The simplest way for us to accomplish this was to shard big customers by metric ID instead of customer ID. This means we pulled big customers out of that 1 big customer sharded topic and put them off in their own metric ID sharded topic. This also involves standing up dedicated consumers for these new topics. From the storage tier's perspective, our queries are also scoped to a single metric using metric ID, and using metric ID here means queries can continue to be served by a single shard, which is good for performance. My bad. So here's a very simplified diagram of our initial setup. We start with a really big storage cluster that handles all customers, sharded by customer ID, and then extract that big customer to their own much smaller cluster, sharded by metric ID. Again, the 2 topics are using different sharding schemes. The main thing here was that we handled the big customer issue without completely changing our entire setup and the existing Kafka topic, because we found some sub-customer size thing that we could shard on. We got kind of lucky though, because our queries tend to involve a single customer and a single metric, so we were able to shard on metric ID. You might have to work harder to find a dimension to shard on, but it's normal to have to get creative for outlier customers. Okay, now it's you.
Thanks. So next problem, once we've solved those big customers, we've sharded coarsely at this point by customer ID, and we sharded finely by metric ID. And we actually have a couple of different sharding tricks as well that we use for extreme outliers, but we don't have time to talk about them today. The point is that there's a lot of different sharding mechanisms which are all hash-based at this point. And it means that the actual shard assignments are basically probabilistic, like any kind of hash function. In order to keep utilization roughly the same across the storage nodes, we rely on chance. It's a good chance, but it's still chance. Given a large number of customers of arbitrary size, each of which has a large number of metrics of arbitrary size, when we hash them across a pool of nodes, we hope that it'll pretty much work out close enough that the difference doesn't really matter, which is the case in theory, but it is not always the case in production, of course. So here's another diagram, similar diagram that we've shown of a single Kafka topic and the storage shards behind it. This is a little bit of a different diagram here. We're showing a single Kafka topic and we're showing the individual partitions within it, but we're not worried about consumers versus Kafka at this point. They're just rows. We're not going to show the individual consumers, and let's ignore the outlier topics that we already talked about. We're talking about the general case here just to illustrate. So to recap, once our intake tier has decided which topic to write the incoming data to, it has to decide which partition to write it to. That's that two-tier system that I was describing before. We can't just spray it anywhere to any partition. It has to end up on the right storage nodes, otherwise we won't be able to find it at query time. The query tier will reach out to the wrong node and the data won't be on there, and then customers are unhappy. That's why we use that Keyfunc that we mentioned before, the same on the intake and the query side. And here is the basic Keyfunc again. It's nice and simple that a customer will always end up in the same partition. And with our second Keyfunc, for those bigger customers that we mentioned, individual metrics will end up in a single partition. Whatever attributes, though, that we hash on, even though there's a really good chance that the number of items in an individual partition will remain the same, there's really no telling how big an individual item will be. So to illustrate, here we have a fixed number of partitions, and there's 3 in this diagram. And that's the n part of the Keyfunc, the number of partitions. So this Keyfunc spreads keys across the buckets evenly, right? And we've got 2 of them in each bucket so far, which is roughly the same amount of load on each. As we add more items, as more traffic goes to this topic, we can see a couple of outliers there in partition 3, that big blue box at the top. It might be a really big customer, or it might be a really big metric inside of a customer. So that partition is already under twice as much load as any of the other partitions, and that includes our consumers behind the topic. It's not an emergency, but it makes auto-scaling a lot more difficult if you've got this pool of things, each of which are on a different amount of utilization. It's much easier to auto-scale these things if they're roughly the same. As we add more items, somewhat predictably, because this is an example of a problem, partition 3 is becoming overloaded, right? Because even though it has the same number of items in it, I think it's 6 items, we got unlucky, and too large of a fraction of the items in partition 3 are really big ones, big customers, big metrics, whatever. So cumulatively, the load on that partition is too high, even though the others have plenty of headroom still. And this is a big problem, of course, overload, like we've spoken about. What we really want in an ideal world is this. It's all of the partitions having exactly the same amount of load, even if that means placing a different number of items in there. You can see partition 2 has some bigger items, but there are fewer of them, and partition 1 I think has the most, but they're all a reasonable size, so they box fit together. We might be able to get that by filling shards randomly with customers or metrics if the size was well distributed. But as you can see here, and this matches reality, the size distribution is not even at all. Fortunately, we are not the first people to need this. This is a pretty common problem with sharding. In 2016, Google released a paper on this topic in which they described an internal system called Slicer, which accomplishes basically this. It's not open source. Their implementation is not open source, and neither is ours for that matter. But we'd like for it to be. But we implemented our own Slicer based on this paper. And we use it to figure out how to box fit the incoming customer IDs and metric IDs into partition based on the load, as I described it previously, not the number of items. And here's basically how it works. The intake can see the size of each item as it writes it, and it reports that off to Slicer so it can understand the load. Slicer performs some sort of magic behind the scenes to allocate ranges of these items, which again is our customer data, to partitions based on the cumulative size of those chunks. And both the intake and query tiers, they receive periodic snapshots of those allocations in order to route, I think Americans say, the writes and the reads to the right place. This is much more complex than just hashing the customer ID, of course. And as a rule, as I'm sure you're all aware, complex things do tend to fail more often than simple things. So we have to work a lot harder to make this complex thing as reliable as the simple thing was. But the trade-off is well worth it at our scale in order to accomplish the partition balancing. So the thing that we learned while we were implementing this is that when it comes to sharding, keeping it simple is the right approach until it's not. Sooner or later, once you get big enough and start storing enough data, the edge cases become significant enough that you got no choice. You got to do something smarter. We did Slicer, but there are a lot of different solutions to this problem. But maybe think about that, just like the previous lesson. Maybe think about that before you really, really need to do it. Even if you're going to be implementing a little bit later, it pays to think ahead on these things. So the next problem, which I think is the last one, and full disclosure, this one's a little less well-formed because we are actively working on this problem right now. This is something that we're dealing with. We haven't really solved it, but we can tell you what we know so far. So the system's pretty complex, right? We've got all these thousands of brokers and storage nodes, and they're sharded into topics and partitions, and they're grouped all different ways, and we have Slicer rebalancing them all actively. So remember this diagram. This is, yet again, a simplified version, of course. We show these two consumers, but there are a lot more, again. We like having so many. We really like having a lot of different consumers because it lets us scale them separately. And it reduces the blast radius of failures. One of the consumers goes down doesn't mean all functionality is lost. It just means that that particular functionality might be lost. And it helps us scale the organization as well. Each of these different consumers, they're owned by different teams who operate independently. But because there are so many, it's really important to us to keep those individual consumers as simple as possible. We don't want to put a bunch of slicer logic in every single consumer. And as such, we keep all that complex stuff outside of the storage tier altogether, so no consumer has it. It exists only in the intake and the query tiers, which, as you may recall from earlier, they're individual services, the hot querier and the points writer, which reach into the storage tier. All of the sharding logic is in there. Those tiers, they both have a single interface to storage, one which knows where to write stuff, and it's based on a sharding config snapshot, and the other knows where to read stuff from, and that's based on exactly the same snapshot. They both read them. All of the consumers in the query tier, the service tier, get to be, storage tier I mean, get to be almost completely ignorant of this. We just give them the data, and then later on we query those same nodes for the data that we know that we stored on them, which is great in the steady state because you want your data, you look up which node it's on, and then you go and query that node, right? But what happens when you want to move that data from one node to another? That's tricky. So here's the basic approach that we take. And it's a clever one or a really dumb one, depending on your perspective, maybe both. From the perspective of a single consumer cluster, and of course, there are many of them again, and we're serving a single Kafka cluster here. We start here in the steady state when everything is balanced perfectly. Whichever sharding scheme this topic is using, we have a bunch of partitions with data flowing through them. Those little pink dots, that's our data, that's our messages. And a bunch of consumer shards behind it are consuming it. Slicer, again, is managing this mapping to keep the consumers really simple. And then on the query end, we examine the incoming queries. We look at who's sending us this query, which metric are they querying for, to figure out which shards have the relevant data. And again, this is managed by Slicer as well. It's very simple. When we want to upgrade that shard allocation, because some of the problems we've shown earlier, some of the partitions getting overloaded, for example, we literally turn up a whole new topic and a whole new set of consumers behind the scenes with no traffic in it. When we're ready, we reconfigure the intake to double write to them. So when data comes in, we write it to the old cluster and the new cluster. If something goes wrong with this new cluster at this point, it's no big deal. Nobody's using it yet. It's just filling up with data. So we can just tear it down and try again if it goes wrong. Not that it ever does, of course. So we wait. We just sit there and wait until it naturally fills up with data. So the old cluster and the new cluster are basically the same, even though the sharding allocations are very different potentially. So the load profile might be different. The actual data that they contain is the same. And then we flip the reads when we're ready to the new cluster. We do this very slowly, of course, not all at once. And once we're confident that we don't need to flip that back because the new cluster works, then we turn down the old cluster. It's very easy. We just tear it down. It is easy, but it's rather toilsome because we do a lot of this stuff manually. We are still working on this, honestly, so we're not going to try and impart any lessons here because we're not at the end of this journey. Except we do know that it needs automating badly. And if that sort of thing sounds interesting to you, automating this kind of workflow, then we are hiring. That's the only sales pitchy thing I'll say for this whole talk. So Tahia, you want to wrap up?
Yeah, so before we wrap up, I'll go over the lessons we learned as we built this thing, and I'm just going to read them. So failure domains are many. Choose which ones to accept. Then we have, you might not need fancy sharding, maybe just multiple levels of the same. Going from 1 to 2 is the hardest, so start with 2 if you can. Of course, sharding schemes don't work for outliers, and that's okay. And then lastly, you're going to need a smart sharding strategy. That's all we got. There is a lot more to say on this, but we only had 30 minutes. And thank you for listening.